Started. Thank you. So, good afternoon, everyone. So, we will start our second session of this day, and again, I will go to very fundamental of the optimization. So, let's talk about a single variable optimization. Okay, so let's assume we have a certain function, okay, which is basically depends upon x, and let's say that this kind of function is basically our fx. So, like, can you identify which one is the maxima and which one is the minima? If I, give certain points here, so let's say this particular point is 1, this particular point is 2, similarly 3, 4, 5, and let's say 6. So, which of these will be a maxima? So, it is clearly visible here. Like, this particular part is our maxima and this is our minimum. So, here basically what we can see is that if certain function, if you look at certain function, the maxima and minima will be basically whenever the slope is 0. So, uh, the optimal values are basically, we can call it a 0 slope points. So we can calculate that slope of this function, like like if we derivate it with respect to x. So this is the slope, and if we make this slope equals to 0, this will give us the x uh, points. Okay. Now the question is, if you look at this particular function, there are basically 6 points you will get. So this x will be like x1 to 6 values you will get for this particular function, because at the 6 places, that's, I think I missed one. Yes. So let's say this is 7. So 7 places you will see that the slope is going to be 0. Out of these 7, there are, you can say that 3 are of maxima, are like peak, and 4 are basically valleys. So depending upon whether we want to maximize this function or minimize this function, we can basically uh, calculate that which values will be the maxima or minima point. But the once we have obtained these values, we have to check or evaluate for all of these 7 values whether the function is minima or maximum. Okay, so we will put these values in our objective function, whatever is the x values. Okay, sorry. Thank you. Basically, let's say single variable optimization. This is let's say one random uh, function fx, which has certain valleys and certain peaks. So you can see out of these, there are certain values 1, 4, 6, and 7 is basically values, and 2, 3, 5 are peak values. And if I want to calculate the maximum value or minimum value, you can clearly see that whenever the slope of this function is 0, we obtain the either peak or valley. Otherwise, there will be some positive slope on this side and then negative slope on this particular side. Okay, so So whenever the optimal values we will get is basically on the zero slope points, and we can obtain the zero slope whenever we basically uh, take a derivative, or basically derivative of this function. So that is slope, and if I make it equals to zero like this, then I will get different values of x, and those values, like in this particular function, I will get 7 values. Then I can evaluate, or basically uh, calculate the function value, where x is basically whatever all these x star values. Okay, and check the decide basically that for maxima or minima points. Okay, so this is basically for a particular function. So if we are basically looking at the slope and all, it's very difficult, or sometimes it's very like what happens sometimes, like instead of this, let's say if I extend this particular one, and it is a straight line for quite some time, so the slope is basically 0 for a quite long time, and those situations basically may also arise, and you will get a very large number of points, like for all of that range of x, the slope is 0. So based upon that, we can like write down some conditions that our del of fx should be 0, and del of x will be 0. This will give you the x star, okay, values of x. So this will give you some x star values, and then whether it is minima and maxima, that we can decide basically like the second order derivative. If it is positive, then it is minima point, that is basically start increasing again, and second order derivative is negative, it means basically it is starting decreasing the values. So we can calculate that, like if f double dash x on these star values is positive, then the point x star is basically a minimum point, and if f double dash star is negative, then it is x star point is basically maximum point. And if again let's check like f double dash x optima, if this value is basically equals to 0, then it is a x star is called basically saddle point. It's neither minima nor maxima basically, so we cannot define it there. Now if I like go into the constant optimization, so like we always have certain constants basically, and we have to optimize that. So for constant optimization, the generalized form of a constant optimization we discussed earlier in the morning, but let's if I look at the constant problems, it's always like minimization of some function fx, and such that, let's say, some condition gx is less than equals to 0. Okay, so I can write it down like there are multiple gx, and then some certain function is there. So whenever there is a certain conditions are there, then it is not like you can minimize the function fx just keeping like first order derivative, but those values or whatever is the x values, they should satisfy this particular condition as well. And it is not a single condition, it's basically many conditions. So in that case, basically we use a method of multipliers, or generally these are called Lagrange multipliers. Okay, so method of Lagrange multiplier, where basically we convert this function into a unconstant optimization, where I can write down fx plus lambda gx. and let's say this is basically a certain g. So if I have many number of constants, I will do it sum equals to 1 to m, and this is for all j equals to basically 1 to m number of equations are there. So this is how I can write it down, a Lagrange function, and you can simply see that this term basically has been placed as a penalty in the objective function. And if I'm minimizing this fx function uh, to be minimum, to minimum value of fx, this term should be 0, otherwise it will be added as a penalty term. Okay, so this is how you can basically signifies this term, and then we will minimize this particular function. So now it's unconstrained, so I can again write down the conditions, and generally these conditions are called basically uh, I can write down the conditions for optimality. Conditions for optimal points. So we discussed earlier that slope should be 0. So to make slope equals to 0, what we will do is we will again take the first order derivative. So I will take a delta L upon delta x equals to 0, and then I will take delta L upon delta lambda equals to 0. So these are the two conditions. Okay, but the thing is, like if I try to solve it, what I will get here is f dash x plus summation over j equals to 1 to m lambda j and gj dash x equals to 0. So this is the first condition. Another condition is basically like, our lambda is also variable now, dual variable. So that will be basically like calling gj x equals to 0. So this part is where it is wrong. That earlier what we defined is that this condition should be less than equals to 0 and not equals to 0. So this is how we cannot write it if there are some inequality constraints are there. Okay. So to give the conditions for optimality, two scientists basically published a paper or their research, and they basically come up with the conditions of optimality, and those conditions are called uh, Kohn-Tucker conditions. Okay, so Kohn-Tucker conditions are basically that it's delta L upon delta x should be equals to 0. Okay, so that is for all, let's say I is my number of variables, so it is like for all I equals to 1 2, and let's say n number of variables are there. So this is I have to write it down for all xi. Okay, then we have delta L upon delta lambda j equals to 0, and that is for all j equals to 1 to m. Apart from that, they have defined another condition that lambda j and gj should be equals to 0 for all j. That the product of this should be 0. Okay, that is condition number 1. And if less than equals to gx condition was there, then lambda j should be a positive value only. Okay, so these were the conditions defined, and once we try to solve these conditions, we basically uh, get optimal solution. Sometimes these are called uh, KT conditions, and you must have heard basically KKT condition. So that is another name, that is Karush Kontukar, and this happened basically like earlier it was called KT condition, then Karush Kontukar, because these two scientists basically they published their work in some year 90s 50s, and Karush already published or basically written these conditions in his I think PG thesis, like few years ahead, or earlier them. That time, I would like, oh, you do not used to publish the work. It was hard submitted in the hard copy. So later it was discovered that Karush already basically uh, identified these conditions. So that name was also added. So this is the different KKT conditions we have to solve the optimal problem. Now, this is so far for the constant and whenever there is a derivative is possible. So if derivative is possible, I can easily solve particular problem. Now, if I look at some linear problem, linear programming problems. In linear programming problems, what happens that if you take the derivative, only constants are remaining, and in that case, uh, you won't get any solution out of it. So all of these, like KKT conditions and all, they are valid for non-linear optimization, but for linear, it is not possible to use those particular uh, problems. Now, if first of all, how we formulate a particular problem. So, if I talk about the formulation, let's consider a example. Okay. So, how we formulate a problem and why we are talking about this is like here I have taken a very simple and very minimalistic example, but when we try to solve the real engineering problems, then we have to think accordingly that each and every aspect of the problem has been uh, dealt with and taken care of. So we discussed the process in the optimization earlier in the morning, and the process is first of all identifying the problem, then identifying the objective and set of constraints. So what are the different parameters which can affect my objective? I have to take care of each and every part. So let's say example, if I take that there are let's say firm, and this firm has some certain products, and these products are let's say A, B, and C. These are the three products, and the prices of these price of uh, per unit is basically let's say 3, 2, and 4 rupees or dollars per unit, whatever we can basically take. Okay, so these are the prices of these per unit. So if firm is trying to produce product A, product B, and product C, he will get a certain profit out of it. Then to produce these products, he has let's say two machines. Okay, and these machines are basically having a like operating time limits. So let's say these machines can two machines are there. Okay, and they have some operation time limit that they can only be worked for certain time. And let's say two machines are basically let's say D and E, and the operation time is, and that is basically let's say 2000 and 2005, let's say minutes only. Okay, so this is the operational time limit of these machines. Now, a machine can produce a certain number of quantities per minute. Okay, So a machine can produce in each minute it can produce a certain quantity. So let's say the how much they can produce is basically, let's assume a particular example. Okay, uh, here it is. Let's say D machine, E machine, product A, product B, and product C. So it takes 4 minutes to produce product A, it takes 3 minutes to produce product B, and 5 minutes to produce product C. Similarly, we can say that let's say 2, 2, and 4 are the minutes needed for machine by machine E to produce product A, B, and C. Okay, so how we can basically formulate this particular problem if we want to do. So first of all, we have to identify our objective function. Okay, so if this is the problem, we have to identify a certain objective function, and what can be the objective function. So uh, obviously, if it is a firm producing some products, the objective function will be uh, either minimization of the cost or maximization of the profit. So I would say here they are basically selling these products, so the uh, maximization of profit will be the objective. And as we can see that, like above, I have discussed that the per unit price is 3, 2, and 4 for these units. So I can say 3A plus 2B plus 4C is the profit which it is earning. Now, what are the different constants? So, different constants are basically like, let's say, if machine D is producing something, it takes 4 minutes to produce one quantity. So, how much, let's say it is producing some A number of quantities, then 4 into A will be the time consumed by machine A. Similarly, 3 into B will be the time consumed by machine B, and 5 into C will be consumed by machine, and same machine. So A, B, and C. So this much time it will take, and maximum this value can go up to like basically 2000. That is the maximum value it can achieve. Okay. Similarly, we can have like your twice of A for the machine B, twice of B plus 4 times of the C, and it can only run for the 2500 minutes. So these are the two constants basically which we are going to see, and then we can make some obligation on these variables as well, that obviously all my A, B, and C should be positive. Okay, we cannot produce negative value, so I can have a positive value, and then maximum limit basically I can place, let's say infinity, that I want to produce as much as possible. Okay, so this is how I can formulate a particular problem. Now, if we try to, yes, thank you. So, this is how we can formulate a particular problem. Now, how we can solve it? So, solving linear problems are basically, there are two methods to solve a linear problem. So if it is a nonlinear problem, we could have taken and the derivative, and like looked at the slope and all. But here we cannot take the derivative. So how we can solve a particular problem? So solution of linear programming problem. So let's first of all like try to understand what can be the different solutions, and what can be the different approach. So I'm just looking at the graphical method first of all, just to understand the different types of solutions available. So like again, let's take an example. Let's say and the objective is to maximize 6x1 plus 15x2 subject to 5x1 plus 3x2, and the limits are, let's say, 15, and 2x1 plus 5x2 less than 10, and both are x1 and x2 are positive. Let's say this is the problem. So how we can solve this particular problem with the graphical approach? So graphical approach is basically like, we should be able to uh, make a graph of this particular entire problem and then look at the solution space. So for two variable problem, it is easier that we can easily visualize the graph, and the graphical approach can be basically useful. But the real life problems are never two variable problem, and they are basically like in power system, and we will have many variables. So we will not recommend the graphical approach, but just like to understand the different sets of solution available. So what I will do is I will create some x1 and x2. Okay, so these are the like x1 axis and x2 axis, and there are two conditions basically. Like if you look at like 5x1 plus 3x2 less than 15. So this is what basically like 30 and 05. So I can draw this particular line. Let's say this point is 3 comma 0, and this point is 0 comma 5. So this is one line, and this line is saying that it is a equality constant. Now 5x1 plus 3x2 equals to 15, and but this condition is saying that the solution space should be 5x1 plus 3x2 less than 15. So I can draw a particular line here that the solution space will be uh, on this particular side. So this line is condition is saying that the solution should be on this particular direction only. It cannot be on this particular like beyond this particular line. So that is point number one. Now if I draw the another line like for the second condition, so we can draw a particular line here, like let's say this one. Like I'm not able to draw it perfectly, so it says up to the scale. Let's say this is 0.2, and this is 5.5 and 0, and this is 0 and 2, and we have some cross sectional points. So by like solving these two lines, we can get a value of like 45 by 19 and 20 by 90. So these values we will get. Okay, so these are the different points, and another point is here 0 0. So this condition also states that the solution space should be below this particular line, less than equals to this particular line. Okay, so these are the two conditions, and they are defining a solution space, and generally we call it feasible region. So if I give you that, okay, can this point be a optimal point? So the answer is no, because both of these constraints does not satisfy it. If I say that can this point be a optimal point, again no, because the constraint 2 is not able to, or basically this point does not satisfy the constraint number 2. So this is how we can basically like first of all plot the possible or basically feasible reason that where is the solution, uh, where the solution can be possible. Similarly, this x1 and x2 should be positive. So I can draw that the answer should be x2 should be positive only. And similarly, I can draw that x1 should also be positive. So these are the condition. And this common region satisfy all of them. So this is my possible feasible solution region where the solution is going like which satisfy all the conditions. So all of these three conditions are like um it this region satisfy them all. So my solution will be out of these. Now I can have to check like look for the maximum point. So usually the solution is at the extreme corner. So I will check for these points, and I will obtain a whatever is the maximum value of the particular solution. One interesting thing here is, so if I calculate the different objective function values for these different points, uh, the let's say f at point 0 and 2 is basically 30, and it is also for the point 45 divided by 19 and 20 by 90. If this kind of case arise, it is basically that the optimal solution will be at this point and at this point, and actually it is on this particular line. So this entire line gives you the optimal solution. So this case is basically like the entire, like the objective function value will be maximum over the entire this particular line. So this is the case of infinite number of solutions. Okay, so we get a infinite number of solutions in this particular case. Okay, so now let's see uh, another example with the some finite number of solutions. So how we can so let's say another example, two uh, certain objective function is there. Let's say maximization of 4x1 plus 5x2 and subject to 2x1 plus x2 is less than 9, and x1 plus x2 is less than 7. Okay, and both x1 and x2 are positive, so I'm assuming that condition is there. If I try to draw this particular, let's say x1 and x2 on this particular side, so I will draw a line like this first of all, and then I will draw a line like this. So here the points are basically like 0 comma 9 is the point number this, and then this is 9 by 2 comma 0 point, then this point is 7 comma 0, and this is 0 comma 7. So this is basically line 2, this is line 1, and both are less than equals to conditions, so we can say that the solution space will be on this particular direction, and for this particular condition the solution space will be on this direction as well. Okay, so we can see that the common region where the and x1 and x2 are positive, so the solution will be on this particular direction. So this is my common solution, or basically solution space or feasible region where I can get the solution. Now I have 4 points. One is 0, 0, another 9 by 2 and 0, 0 and 7, and one intersection point which is 2 comma 5. Like if we solve these two lines uh, the equation, we get this point of intersection, and the values are basically 2 comma 5. And once we try to get the value of this objective function 4x plus 5x2 for these four points, we get to know that the x star or optimal value is basically at point number 0 and 7. So we can say that the x1 is 0, x2 is 7, and the function maximum value is basically, if I put these value, it is 35. Okay, so this is my optimal point, maximum point. Okay, can you please, so there is a question, can you please, how you are considering the line 1 and line 2, on what basis you decided? Okay, so I thought, like this is very fundamental, so I was just quickly going over it. So how we are drawing these lines? Okay, let me change the color. So the first inequality constants, I will make it like this. Okay, equals to 9. If I put x2 equals to 0, the x1 value will be, so like x2 equals to 0, so the x1 will be 9 by 2. So this is the point here, 9 by 2 comma 0. If I put x1 equals to 0, x2 will be 9. So this is the another point, and it's a straight line. So once I have obtained 2 points, point number 1 this, and let's say point number 2 is this. So this is point number 1, point number 2. So I can draw a line, and this is line number 1. Now if I look at the arrows, how I'm making the arrows. So let's assume any random value, a random point on this axis, and let's say 0 0 is the point. So let's put this 0 0 in this particular condition. So this is a equation 2x1 plus x2 less than 9. If I put 0 0 here, I get 0 less than 9. Okay, so this satisfies the part that origin, wherever origin is there, origin will satisfy this particular condition. So arrow should be towards the origin. So that's why I'm making the arrows towards the origin here. Okay, if this line could have been, like let's say 2x1 plus x2, instead of less than, it is greater than 9, then in that case I would have drawn like this. Let's say a certain line is there, and the same line is, let's assume this is the line. In this case, for this particular case, uh, if I put 0 0, which is this point, 0 comma 0, and if I put 0 0 here, it becomes 0 greater than 9, which does not satisfy the condition. It means this point is not in the uh, range of this particular basically condition. So I can say that the feasible region will be on the opposite side, and this side is not feasible, and this side is basically feasible. So by putting, like origin or any, sometimes what happens that like in these lines basically passes through the origin. In that case, you can put any point either side. If it satisfies the condition, the arrows will be on that point side. If does not satisfy the condition, the arrows will be on the other side. So this is how you can identify the feasible region in the particular problem. Okay, let me maximize it. Okay, and so similarly, we have drawn the another line, and like point of intersection. We give me like if we solve these two equations all together, we will get 2 comma 5, and we will get 5 points, and this is the like one solution f maximum. Now, why we are talking about these parts is basically that I wanted to show you that a linear problem can have certain types of solution or certain basically number of solutions depending upon the nature of the problem. So what are the different solutions possible, or I would say outcome of a LPP? So the very first outcome is basically we have seen it as well, like the we had an infinite number of solutions. There was a line where for which like if you pick any point on that particular line, you will get the same maximum function value. So the entire line is basically solution space, and on a line basically you can have infinite number of points. Second example, this like the above one, we obtained a single solution. So we can say that outcomes are basically a definite and unique optimal solution is possible. Okay. Second case, which we have already discussed, that an infinite number of optimal solution, and in that case you can pick any solution, all will have the same objective function value. Then we have a third case, which is basically unbounded case. unbounded solution. Okay, then a case is possible when there is no solution at all, and sometimes which is basically the part of the first category, but we can call it another basically single solution. So how unbounded solution or no solution or single solution are basically possible. So if we look at about these and talk about this, so I will just draw certain solution space only, and you can with the conditions equals to less than and greater than, you can easily formulate those conditions whether it is less than or equals to. So we have discussed the case one where basically unique solution and uh, unique and single solution was a definite solution was present. Now if I look at the unbounded solutions, let's consider the same example. Let's say there is a one line here, and let's another line is on this particular side, and they have the solution space. Let's say this condition was of, instead of less than, it was of a greater than condition. In that case, you will basically see that uh, arrows will be on the opposite side. Similarly, this condition was also be of, let's say, greater than type, and you can see that the solution is on opposite side. And all the our x1, x2 are positive, so I can say that like this will be the solution space. So the feasible region is basically like which satisfy all of these four conditions is this, and it is going up to infinity. Okay, so here the feasible region is unbounded, and those kind of solutions are called unbounded solutions. So this feasible region is unbounded, and if I look at the points available here, so some point, some x1 and x2 point will be this. Some point here where x1 is 0 comma some another x2, okay, dash, let's say. And then I have a point, let's assume at the infinity, which is 0 comma infinity, and some point, extreme point will be at infinity comma infinity. So these are the different points available. If I just look at the corner points or extreme points, if this problem is of minimization, then maybe 0 x2 dash or x1 x2 is optimal. Okay, so the optimal solution is maybe 0 x2 dash, because here the point will be the solution will be minimum, but at these infinity it won't be possible, and the solution is undefined at always. But if I make the objective function is maximization, the solution is unbounded, that you can go whatever distance you want, and your feasible region is unbounded. So in this case, this is the case of unbounded solution. Now let's talk about uh, no solution case, when there is no solution is present. And let's draw something. Let's say in no solution case, basically, let's that is a good example. So let's see, this is my x and y axis. So one line is this, and another line is let's say this. Okay, so in this case, wait. Okay, so let's say these are the two condition. Okay, this is let's say condition one, or this is basically the condition two, and it says that the solution should be on this side. If these are the conditions, and this says that the solution should be on this side. So if you look at these two conditions, they don't have any common solution. Or do they have certain common region? Which part is common for these two conditions, condition one and condition two? Is there any common region which satisfies both the conditions? Anyone? So if you look at only these two conditions, this particular region satisfy both the conditions. Okay, that this is also saying that the solution should be in this direction. This condition is also saying that the solution on this side, and this is saying that solution should be on this particular direction. So yes, this region satisfies it very well. But usually we have as this non-negativity conditions that x1 and x2 should be positive. So this will say that your x should be positive. So it will be in this particular direction, and it will say that the x should be on this particular direction. And these two conditions, non-negativity, uh, chokes out this particular common point, and you will not have any point, or basically any region which satisfy any of these conditions. And if there is no region which can satisfy the conditions, you will not have any solution. So no solution or no feasible solution basically is the output. Similarly, like if I want to draw another diagram, let's say there are two lines. Let's say one line is this, another line is this, all the parallel lines, and this is saying that the solution should be on this direction. Another one is saying that the solution should be in this direction, and if they are parallel, they will never interact, and you will not get any solution at all. So this is a no solution case. Sometimes a problem is like in such a way that you get a single solution as well, that you don't constraints are in such a way that there are no multiple, or basically not even if the feasible region is not present, only a point is there which satisfy the whole condition. So single solution, and whatever is that solution, whether it is minima or maxima, it doesn't matter, that will be our solution. So let's say if I have this kind of equation, let's say one condition is that your solution should be on this particular direction. Another condition is saying that the solution should be on this particular direction. Okay, and uh, non-negativity, we can say that the solution will be on this direction, this direction, and this direction, and this direction. So the common region which is possible for if I talk about let's say condition 1, condition 2, and these are also non-negativity conditions, so I can say condition 4 and condition 5. So this region is basically common region which satisfy everything, and you can get a solution. But let's draw another line which basically passes through this particular point, and this says that the solution should be on this particular direction. If this condition is there, then this region which basically which we have identified so far is also not a feasible region, and there won't be any solution. And you can see that only this particular point satisfies all the conditions. So only single solution is available, and that will be this particular point. So these kind of different solutions are basically present. But this is okay that for two variable problem we can visualize it, we can understand like what are the different solutions possible and how basically we get it. But it's not a way to solve a particular problem. We need basically proper method. So a method called simplex method was developed, and it is basically programmable, that you can write down a program for this. It is a programmable method. And somebody asked me like what solvers we should use. So on this method a solver was developed, and that is called simplex. So simplex solver was basically developed, which is robust and best solver to solve a linear programming problems. So I will not go much into detail about the simplex method. I will just quickly guide you or just give you a glimpse for a very fundamental problem. And like there can be different techniques, different begin simplex method, and there are two-phase simplex method. So there are different variants as well, and those are based upon the nature of the whether the constraints are less than equality constraints, inequality constraints. So based upon that there are different variations in the simplex method, but in general simplex method is perfectly fine. So let's consider an example. There are many faculties from the institute, different colleges there. So how simplex method works, we can talk about that. It's very simple, let's say certain objective is there, and let's say 4x1 plus 5x2, and certain conditions is there. So x1 plus x2 less than 3, and then x1 plus 4x2 3x2 less than 10, and x1 and x2 are greater than 0. Okay, let's assume this is the uh, problem which we want to solve. Now, to apply this particular method, or basically we have to convert this entire problem, and we have to get rid of these inequality constants, because as in linear programming as well, and we obtained that whenever we are trying to solve our objective function, the solutions are always on the boundary, not in between. Okay, so boundaries are basically point of intersection always. There are multiple conditions. So these conditions, in case of linear system, let's say two variable, they will create a line. Otherwise, they will create a plane only. So those are basically point of intersection of different planes. If it is two variable, it is lines. Otherwise, multiple planes will be interacting, or will be having a point of intersection. So the solutions are always on the point of intersection of different conditions. So to obtain the point of intersection, we have to convert everything into equations instead of the condition, because the point of intersection will be at the equations level only. So what we can do is x1 plus x2 is there, and we will add some slack variable so that this slack variable in such a way that it is basically uh, makes the less than condition to a equality condition, that x1 and x2 was less than 3. Now if I add something into this, it will become 3. Okay, so this if x1 plus x2 is equals to 3, then s1 will become 0. So that satisfies the condition. Similarly, 3x1 plus 4x2 plus some another variable s2 is equals to 10. So we can write it down like this, and same we can put it in the objective function x1 plus 5x2 plus 0 s1 plus 0 s2. So these are the basic fundamental formulation. Now, how we can use these formulations? So there is one a simplex table which I'm going to use. So I have already drawn it earlier. So let's say for this particular problem, I have to define first of all these two equations. So let's say define equation 1 and equation 2. So the equation 1 is basically here. I can say that it is equals to 3, and the multiplier of x1 is 1, multiplier of x2 is 1, s1 is 1, and there is no s2 in the equation number 1. So this is what basically we have equation number 1. The second is it is equals to 10 and 3, 4, 0 and 1, I think. So this is, I think, understood by all. Now let's look at the objective function. So objective function generally we call it like maximization or minimization of cx. So this c is basically the objective function value. So the x1 multiplier is 4, x2 multiplier is 5, and then s1 and s2 multipliers are 0. So I have placed this one as well. And what happens that if you look at this particular problem, there are two conditions and four number of variables. So uh, the ranks are basically different. Like with only two conditions, we cannot solve four variables. So what we have to do is whenever there is a solution space or like these kind of equations or constants where variables are more and basically constants are less, then what you have to do is you can only solve the variables which are equals to number of constants. So if there are two constants, you can only get two values here. You the all the other variables values will become 0 at the end. So in that case, basically the entire matrix or whatever is the, like this matrix A x equals to B, this kind of matrix, uh, we have to take basically a part of it generally, and that m by m matrix should be like whenever we are trying to solve the matrix and finding out the value of variable x, it is always like inverse of this A matrix and to B. So it should be able like we should be able to take an inverse of it, and we don't know whether we will be able to take the inverse of x1 and x2 with 3 and 4, like x1 plus x2 and 3x1 plus 4x2. So it's easier to like we can easily take the inverse of this one, that 1 comma 1, it will always have a determinant of 1, so inverse is possible. And we can assume that the s1 is equals to 3 and s2 equals to 10. So s1 is assumed equals to 3, s2 is assumed equals to 10, and x1 and x2 and x1 and x2 in this is basically initially assumed equals to 0. So we have assumed our basic variable s1 and s2, so that these are my basic variables. So I have placed them here in BV, basic variable. So I have assumed that these are my basic variable s1 and s2, and the value of these basic variables will be uh, 3 and 10, 3 and 10, and all the other values will be 0. So if I put x1 x2 0 here, s1 will become 3, so this satisfies this condition. X1 x2 is 0, this satisfies this condition as well. Okay, and this is my initial starting point, that my basic variables are the slack variables. Then the coefficients of basic variables in the objective function. So if you look at in objective function, the basic variable coefficient is 0 0, so I will put a 0 0 here. Now first of all we have to calculate the zj minus cj, and here the zj minus cj is basically cb multiplied with x1, and we can say like x minus multiplied with cj. Okay, so let's say I'm talking about jth term, so I will put a j here as well. So you can see, like, the very first term is basically uh, this particular part will be like, 0 into 1 plus 0 into 3. So the first and second line minus 4. So this will give you the value of minus 4. So I will place it minus 4 here. Then the second part here is basically what? It is basically 1 multiplied with CB, 4 multiplied with CB0, and minus 5. So I can say that it is 0 into 1 plus 0 into 4 minus 5. So this will be the minus 5. And then the third part is basically again 1 multiplied with 0, 0 multiplied with 0. So 1 multiplied with 0 plus 0 multiplied 0 and minus coefficient Cj. So that is also 0. So it will come equals to 0. And similarly, this part will also be 0. Now we have to look at the Zj minus Cj are the minimum of basically minimum of all. So this part is basically my minimum value. So I will keep this column available and I will do xb upon x2. So xb upon x2 is basically here it is 3 by 1, which is 3, and then it is 10 by 4. Okay. And if you look at the minimum of these two, so this term is minimum. So I can name that my S2 is leaving the basis, and X2 which is entering, so it will be entering the basis. So I will place them in the next part. So in the basic variable, I will keep S1 as it is. Then instead of X2 will become here. Now there is one more thing. Coefficients will remain same. So it is 4, 5, 0 and 0. And once basic variables has been identified, the coefficients of this will be calculated. For this entire matrix, basically we are now doing as some kind of factorization so that x2 should get certain value. Okay, so what happens, like, s1 and s2 will have some value and rest of the others will be 0. So if you put like in this particular these two conditions, S1 and S2 available and x1 equals to 0 and s2 equals to 0, and try to solve it, what you will get is basically certain value of x2 and certain value of x3, and it has been programmed that this becomes a key element here. This 4 is becomes key element, and to get this solution, just like s1 and s2 was 1, I have to make x2 equals to 1. So to make x2 equals to 1, I will divide this entire row with the 4. So this will become uh, 10 by 4. This will become 3 by 4, and then it's 4 by 4 is 1, 0 by 4 is 0, and then 1 by 4. So this is what I will get. Now, just like these 1 and 0, like s1 and s2 had only one value with respect and others was 0. So I have to make this value equals to 0 first of all. And to make this equals to 0, I can do this like matrix manipulation in the row respect to the row. So what I can do is I can subtract this from this divided by this particular 4. So in that case, basically what you will get is 3. So here it will be like what I can do is the r1 new is basically r1 old minus r2 old divided by key element, and so this becomes 1 r1 old So just wait again. So what we can write it here is basically, like I have to make this particular zero. So I can say that this R1 new is equals to R1 old divided by whatever is R1 with respect to key element uh, value. So this makes this equals to 1. Once this has been made equals to 1, I can subtract the R2 new out of it, and this will make it equals to 0. Okay, so there are multiple ways of doing it. I just have to make it 0. So just like the R1 new is R1 old. R1 old was 3 1 uh, 1 1 and 0. So this vector was the R1 old divided by the key element with respect to this in the old one was, so this was the key element 1 minus R2 new. R2 new is 10 by 4, 3 by 4, 1 0 and 1 by 4. And if you do this calculation, you will get the new value of R1. So this is 10 minus 3, 12, 2 by 4, 2 by 4. Then I will get 1 by 4, 0, and then 1 and minus 1 by 4. And once again, if you calculate these values, Zj minus Cj, so I would just like put this here. Zj minus Cj, it is basically 0 into 1 by 4 plus 5 into 3 by 4 minus 4. Another is 0 into 0 plus 5 into 1 minus 5. Another is 0 into 1 plus 5 into 0 minus 0. And then last one is 0 into minus 1 by 4 plus 5 into 1 by 4 minus 0. And these values are basically, if you solve it, it is basically 1 pass 5 15 and 16, so minus 1 by 4. So this will be minus 1 by 4. And similarly, I have calculated it is 0 0 and 5 by 4. And we will solve it here. I can see that the negative value is this particular value, and based upon these factors we can calculate the minimum ratio, and that will be 2 by 4 divided by 1 by 4, and that will be equals to 2. And this will be basically 10 by 4 divided by 3 by 4, so that will be equals to 10 by 3. So the minimum will be 2, and this will become the key element, and S2 is leaving, so I can say S1 is leaving the basis and X1 is entering. And we will solve it until all the Zj minus Cj are positive or 0. Okay, so we will solve it until all the Zj minus Cj are positive and 0. And if you solve this particular last table, it's basically 0 and 0. And then 4 5 x1 x2 and xv will be 2 1 1 0 4 minus 1 and 1 minus 3 1 0 1 minus 3 and 1. Once you solve it, you will get this kind of solution. And then once I calculate the Zj minus Cj, it becomes 1. So here basically all Zj minus Cj are greater than or equals to 0. So we will stop the solution, and basic variables are basically the optimal variables, which basically gives the optimal value. So in basic, x1 was there and it will be equals to 2, and x was 1 there. So this is the optimal solution. Okay, so this is how we can solve it. This is the one, it's just simple glance that how we solve this particular uh, simplex method. So if you have so far any doubts, you can ask. Then we will move to basically certain power system problems, and then we will look how we can solve them. Any doubts so far? You can raise your hand if you want to ask any question. If you have any doubts so far, we can discuss. So I will just if you think if you have any doubts, you can always put them in the chat. I will just take a quick 1 or 2 minute break, and I will resume. So won't go anywhere. I will resume in 1 or 2 minutes. So yes, I will share the this notebook, and as well as WhatsApp group. We will share the this YouTube link where we are streaming right now. So this is very fundamentals, just to all of these exercises to visualize how the problems are, how we can handle the problems, what are the happening inside the solver and all, just to give you a quick glimpse about it. Now tomorrow there will be Dr. Deep Kiran will be there, and he will be discussing uh, non-linear programming. And so before going into non-linear just conventional or mathematical part of it, I would like to explain you one very fundamental system problem, which is economic load dispatch. Okay, so we will discuss the economic load dispatch now. Okay, so it's visible, right? So let's see. So if we look at the economic load dispatch problem, first question which comes is, what is economic load dispatch? So what is like very fundamental economic load dispatch problem? Anyone wants to answer? It will be better, like if you keep on asking something, then like the discussions are always healthy. You will learn something new as well out of the discussion. Otherwise, whatever like I have planned, we will learn that only. So anyway, so economic load dispatch problem is we have certain units and we want to dispatch those units economically such that these units satisfy or basically fulfill a particular load. So let's say there are n number of generators are present in the system, and a total demand of, let's say, PD is my total demand. So in that case, how a system operator will dispatch the generators? He have to make certain decision that he have to supply the particular demand, and yes, thank you. So like as mentioned by Ratan, that the operating cost should be minimized. So the system operator has to supply this demand of PD, and he has n number of generators with him. So he will use those n number of generators in such a way that the cost is minimum. Okay, so he will try to minimize the cost. So the ELD problem is basically minimization of total cost, and that will be like like we have n number of generators. So let's say I equals to 1 to n number of generators, and certain cost function is there, and let's say Pi is the production of that particular unit, and subject to that this production, whatever units they are producing, this should be equal to the total demand. So this is our economic load dispatch problem. uh, as per like optimization problem is concerned, I have to place the variables here, just to clearly marking that okay, these are my variables. So under the min or max function, I have placed that okay, these are the values which I am looking for and are basically in which I am interested. So Pi is my decision variable, that how much each unit should produce, and the objective function is minimize the total cost, which is given by this. Apart from that, we can have further constraints that Pi can be basically less than Pi maximum. So whatever is the maximum capacity of the unit, it should produce less than that. And there are always, like sometimes minimum capacities of the unit, so it should produce for all uh, like minimum more than the minimum capacity of the plant. And then these conditions I have to write down for all, let's say, set of n. Okay, and here n is basically 1 2 and up to n. So this is my objective function. So the constant number 1 is objective function, constant number 2 is power balance equation, and then I have a constant number 3, which is uh, basically our power generation limit. So This is the constraint number 3. So this is minimization of cost. This equation number 2 is called power balance equation, and these are basically power generation limits. Can somebody tell me if there are 10 number of generators? If there are 10 number of generators, how many power balance equation I will have, and how many inequality constraints I will have for 10 number of generators? You can type your answers. Yes, so the answers is one power balance equation and 20 inequality constraints. So, you know, I always ask this question, and like people get confused that okay, there is only one, so one constraint and one constraint is this. Sometimes they call it like okay, if there are n number of generators, the constraints will be n. But this constraint is basically not a single constraint; it is two. One is upper limit, one is lower limit. So we will have 2 into n number of inequality constraints. Now, as we already discussed, that this can be solved. Okay, so as we already discussed that this is okay. Can somebody tell me whether it is a linear or non-linear? So we have different classification, constant or unconstrained. So I can see there are conditions. So it is a constant optimization problem. Now, can somebody tell me whether it is a linear problem or non-linear problem? So Anand is saying that it's a non-linear. Which Anand, which equation is non-linear? Can you put number? I have mentioned 1, 2, and 3. Power balance equation number 2. Gagan is saying that non-linear of the quadratic cost functions are used. So Anand, this equation number 2 is linear itself, because like if I have to write it down for let's say 2 or 3 generators, this entire part can be written down like this. This part can be written like P1 plus P2 plus P3 equals to some demand. Okay, and this is a linear equation. So equation 2 is very much linear. If I talk about equation number 3, it is again like some we are writing like this, that P1 is less than let's say 100 megawatt and more than 20 megawatt or something like this. So yes, equation number 3 is also linear. But if I talk about the objective function here, this basically create or make this problem, you can say, linear or non-linear. Okay, so if this ci pi is let's say so this is a function, it's not like multiplication of ci and pi. It is a function which is in terms of power generation. So if I say that this is let's say some bi into pi, then it is linear. If I say this is ci and pi equals to uh, raised to power let's say n, and p raised to power n plus a raised to power an minus 1 p raised to power n minus 1 plus so on, and you can say that it is at the end it will be a1 and so 1 plus a naught and p naught. So this is how we can write down the entire equation. Okay, so how the cost of a power plant are basically like thermal units we are talking about specifically here, which is like coal fired or nuclear power plant based. So what nature do they exhibit? The cost function of a unit power plant or power unit. So basically they are non-linear in nature and they are highly non-linear, but we out of like this is like we can write it down in generalized way where this n, okay, this n is different, this is just power, and approximate we can say that it is generally ap square some bp plus c, and we can call it a quadratic cost function. Okay, so generally the cost function is quadratic, assumed as a quadratic cost function, and if because of this p square term here, this entire objective function is become has become the non-linear. So I would call it non. The nature of this problem is non-linear, and so economic load dispatch is basically a non-linear NLP programming, and as the constants are linear, it is also called as a quadratic programming problem, which we understand like gone through or like covered earlier in the morning class. So it is a special like specific LPP, a linear programming problem. When all the conditions are linear, then it is called quadratic programming problem, QPP. So now how we can solve it? So we know that the methods of Lagrangian multiplier we will adopt. So it is basically method of Lagrange multiplier. Let's assume. Okay, so I will put down some Lagrangian multiplier. Pi is my variable, lambda will become another variable, and I would put that summation of I equals to 1 to n ci and pi plus some lambda pd minus I equals to 1 to n and pi. Okay, so this is what I will place that equality constants with the this particular function, and then we can solve it. So we can calculate the lambda L upon lambda pi, and we will make it equals to 0. So that will be basically delta ci pi upon delta pi and minus lambda. Okay, so this will look like equals to 0, and this we have to write down for all I set of n. So a number of generators, for them we have to write it down. Similarly, delta L upon delta lambda, so that will be basically equals to 0, and if we do this, it is basically PD minus summation of I and Pi equals to 0. Okay, so these conditions we will have, and as I again asked that, okay, for 10 number of generators we will have 11 number of equations, but the variables are like 10 pi and 1 lambda, so we can easily solve it. Okay, so once we solve it, we get the values of pi and lambda, and that will give us the optimal value of solution. Here if we have assumed this particular equation as a quadratic function, I can say it is basically tau ai. So the derivation of this will be like quadratic function. So this is the quadratic function, and the first order derivative will be 2ap plus b. So I have placed it here like this: 2ap plus bi minus lambda equals to 0. Okay, so we can write down the conditions that lambda equals to 2ai pi plus bi, and for all I sets of n, and pd minus summation of I pi equals to 0. So these equations we will solve and we will get a solution out of it. Now, why and what happens here basically, you have to look at the problem. If maximum and minimum limits are absent, because we have not considered them in the Lagrangian function. Like here you can see we have not considered any maximum or minimum limit. So if we solve it that these variables are unrestricted, uh, then this will give us the perfect solution. Okay, so if absent, we can solve above equations. We can easily solve the above equations, and we will get some value of pi and lambda I. And if you can see that, let's say this lambda is nothing but del ci and del pi upon del pi. Generally we call it incremental cost. Okay, and ic is incremental cost. So, incremental cost of generator I. Okay, so this is we have to write down this for all I. So I can say that lambda is equals to ic1, lambda is equals to ic2, and so on. So we can say that lambda is equals to ic1 equals to ic2 equals to icn. And this says that the incremental cost of these generators is equal or should be equal at the optimal point, and all of these generators will have the same incremental cost. So what incremental cost signifies? So if I what is the significance of the incremental cost? If I talk about, so incremental cost is basically, you can say that uh, change in cost, okay, with respect to increase in power. That's is incremental cost. Okay, and so let's say delta cost divided by increase in power, so that will be also P, and this is basically called price, which is the unit is basically, let's say, dollars per megawatt hour. So this gives you the price, and in this particular case I generally call it system price as well. Okay, so I generally call it system price. So I can assume that the lambda is basically the system price. Okay, so we have defined that the lambda is a system price in this case, and in this particular you can solve certain problems out of it, and you will get a certain particular solution. Now, what happens if limits are imposed? If limits are placed, what will happen? So if you look at this particular equation here, from here we can calculate the power. Okay, so you will get like the unconstrained case, you will get certain power P1, P2, and P3, and like all the generators power and certain lambda. And if generator, or basically like the power output of a generator is coming out beyond the whatever is the limit, then we cannot accept that particular solution. Like with the graphical method as well, we have identified that our limits, all the constraints should be like satisfied. So if that variable is like in unconstrained solution, if it is going beyond the um, your limit, then we will enforce those limits. So how we can solve, let's say, so we will if limits are placed, then the solution will be like first step is we will calculate, or we will optimal schedule without limits. Okay, then we will check for limit violation. Okay, now there are two cases basically. Let's say some generator is violated, that whatever is the pi is more than whatever is the pi max. In that case, what we will do is we will make this pi equals to pi max. Okay, and generally like by thumb rule, we perform that if this generator is the pi is coming out whatever is the minimum capacity, we generally should do the same, that this pi should be equals to minimum, but this is not a correct practice. So let me solve a particular example. Like we are using this book Wood and Woolenberg, and let's understand with a particular example. Otherwise, like how we can solve it. So certain post functions are given, like C1, P1 are given equals to like 561 plus 7.92 P1 plus 0.001562 P1 square. So this is the certain post function. Similarly, we have another post function of the like 310 plus 7.85 P2 plus 0.00194 P2 square. Then C3 is basically equals to 78 plus 7.97 P3 plus let's say 0.00482 P3 square. And some generation limits are also mentioned, that this P1 should be less than 600, P2 should be less than 400, okay, and P3 should be less than 200. And then they have a minimum limits as well, which is like 50, 100, and 150. And the total demand was, let's assume the demand is so we will consider this particular example, and let's assume the demand is roughly around 850 megawatts. So if we write down those conditions, like solution, if we talk about, we will write down the conditions, and then lambda. So we will have four equations and four variables. Okay, And in this case, the solution will be like, lambda will come equals to 9.148, and P1 will be coming 393.2, P2 will be 334.6, and P3 will be 122.2 megawatts. So if you look at this particular solution, everything is fine. P1 is also within the limit, P2 is also within the limit, and P3 is also within the limit, and some certain lambda is also provided. Now, what happens that, just change this particular example. If we change the cost function of C1, P1 equals to 459 plus 6.48. So we are basically making it cheaper, okay, as compared to the existing cost. So 0.00128 P1 square. If we assume this particular thing and rest of the data is same, the lambda will be basically 8.284, and P1 is 704.6, and P2 is 111.8, and P3 is 32.6. Now, what we should do here is basically like, if you look at the limits, the first generator has a maximum limit of 600. So this has been clearly violated. Second generator has 100 to 400. So this is fine. And the third generator has the minimum of 50. So it is basically should be it is less than 50. And this is basically P1 is, it should have been less than 600, but this should have been more than 50, but no, the answers are different. So what we do is like, as explained, that what we can do is we can keep it P1 equals to 600 and P3 equals to 50, and once we do this, P2 will automatically be 850 minus 600 minus 50, like, it's a power balance equation. So it will become 200. So is this solution right? So again, I would say no, because whenever, if so, if maximum limits violates, enforce that limit. So if maximum limit is violated, we should keep basically the generator to that particular value. What happens here, like, if you look at this particular, why this is basically coming more than 600 and why this is coming less than 50. So can you tell me why this is happening here? Like, why this is coming more than 700? Anyone? What is the significance of this one? Like, why it is coming more? And if it is coming more, what it signifies? What is the meaning of it? Yes. So the cheaper power is available in P1. So that's right, that the generator one is very cheap as compared to the other two, and generator 3 is expensive. Okay, so that's why the optimization will try to get as much power from generator 1 which is possible. So that's why it is coming equals to, like, more than the capacity, because the conditions we have written is without the maximum and minimum limits. So we will get this. Now, another way of looking at the problem is look at the system price. So this is the system price which is coming right now, And if I enforce this limit, let's say if I make it 600, what is the lambda 1, or I could say incremental cost of first generator, and that will be 2 AI pi plus bi. And if I put that value here, what will be the lambda? Okay, so if I put the 600 here, you will get a certain value. And can somebody calculate it? Can okay, and okay, you need data, but let's not calculate. Can somebody tell me that what will be the relationship between, let's say, this lambda 1 and the lambda which we have obtained, like right now, this particular value here, this 8.284? What should be the relationship? Less than, equal, greater than? So you are saying, Moise is saying the lambda 1 will be more than the this current lambda, which is like 8.284. So let's check it. As we have, like I have explained that this lambda represents the system price. And let's talk about a simple economics, and like how the economics will work. So if prices go high, uh, suppliers will try to produce more so that they can sell at a high price, and if prices go low, they will sell less. That is very fundamental economics. And that is also, you can put that it is also optimization, like decision making will be based upon the prices. Right now, like like gold and silver prices, based upon that, people are either buying them or selling them. So if it is a very high price and you want to sell that at particular price to make some profit, yes, so decisions are driven by the prices. And based upon our own self conscious, we optimize our objective and we take certain decision. Here as well, this lambda is price. So there is one comment: 10 104.6 power of P1 will be delivered by a higher cost generator than P1. Yes, so I'm coming to that part, that if certain lambda 8.284 is there, and for that particular lambda, uh, generator 1 is producing 7046. So its incremental cost is basically equals to 8.284. Now, if I reduce the power, just see here, this was equals to lambda, and that's roughly around 8.2 and something, and this p was roughly around 704 and 6 value. If I reduce this particular p and make it equals to 600, it means the incremental cost are basically, this lambda is also incremental cost of first generator, so this will also reduce. So the incremental cost will reduce, or I can say that now this lambda is not equals to the incremental cost of the one. So the lambda 1, or the incremental cost of the first generator, will be lesser than the current lambda. Okay, that it is producing less, so its incremental cost should be less. Now, what happens here is basically, this is clear that this is a cheaper generator. Its incremental cost is very much less than the system price or the lambda. So this is like I'm calling it system price. So if it is very much less than this value, it should produce the maximum power output, and that is equals to 600. Now, can I, if minimum limit violates, we can enforce that limit as well. Okay, so if a generator is basically violated the minimum limit, we have to make sure that it should produce certain minimum value. In that case, the lambda incremental cost of that ith generator will be more than the existing system price. That its cost is higher, but still to satisfy the constraint, we have to take certain minimum power out of it. But if some generators, if some maximum limit and minimum limits are violated, let's say both the limits are being violated, what will happen in that case? And that is the case with the current example, that both P1 and P3 has been violated the limit. So if only minimum limit is there, then it is fine, we will enforce that limit. If it is maximum limit, we will enforce that as well. But both max and minimum limits are violated. In that case, which limit we should basically fix first of all? So whenever this kind of situation happens, we will first fix maximum limit, which is cheaper generation, and recalculate economic load dispatch. And we will again calculate the economic load dispatch, because once we fix a maximum limit, certain production, let's say like instead of this 104, roughly around 104 megawatts power is more this generator is producing, and if I'm enforcing this 600 limit, this 104.6 megawatt has to be produced by P2 and P3. So we have to re-dispatch everything, and we have to recalculate everything. Okay, so we should basically enforce only maximum limit if this is happening, and then recalculate again, check for that, and this is how we solve it. Another way of doing is basically, instead of uh, looking at this problem like that, what we can calculate is, we can calculate the incremental cost of the ith generator. If the incremental cost of ith generator is equals to lambda, and let's say the very first case where all the three generators were within the limit, and the increment cost of each generator was equals to 0. So the basic fundamental problem which we have formulated here without the limits was this, right? This particular problem, if you can see, we did not considered any limit, and if we get the solution of this one, this condition is saying that the lambda should be equals to the incremental cost of the ith generator, and the power balance should be matched. So it says that all the incremental costs are equals to lambda, that is without any limit violation. So I can same thing I can write down, that if incremental cost is equals to lambda, the ith generator is producing between the maximum and minimum limit, that there is no limits has been violated. Let's say if ith generator is kept at the maximum capacity, so just like we assumed, So that will be the case when the incremental cost of the generator is less than lambda. So whenever the incremental cost of the generator is less than lambda, that generator will be kept at the maximum value. And similarly, if the incremental cost of the generator is more than lambda, then we will keep the pi equals to minimum limit. This part you can simply understand by the economics as well, that whenever incremental cost of the generator is equals to the system price or the market price, it will produce within the limits, and it will like whatever is the optimal value out of the economic load dispatch, it will produce that value. So there is no fixed value that it will be, either it will be at maximum or minimum. It will produce some value depending upon the problem and depending upon the demand. But if you look at here, second condition, which is this one, if incremental cost is less than the system price, so a production cost are the, like, for next megawatt is basically incremental cost. If that cost is less than the market price or the system price, the generator will produce more because it will get benefit. The market price is higher, cost is less, so it will produce more, and it will keep on producing more until it reaches to the maximum limit. So that's why the pi will be at the maximum value whenever the incremental cost of the generator is less than the system price. Same, the other way around is whenever the incremental cost of the generator is more than the market, it is basically not getting any money. It is in the loss because the cost is more, and as compared to the our um, market price. So the incremental cost is more than the incremental price or incremental system cost. It means that this generator should produce as much less as possible, and that will be at the minimum limit. So that's why pi should be at the pi min. Okay. So this is it for today. I think we should take the break. If you have any doubts, you can ask. Feel free to ask. You can raise your hands. I will try to answer them. We will unmute you, and we will have the like answer the questions. Do you have any doubts? I will yes, definitely share this note with you, and a video lecture streaming link will also be shared with you on the WhatsApp group. So you can always rewatch the videos, like if something is missing, and if you are not able to understand some part, you can always rewatch them. One more thing is, you can always email me if you have any doubts. You can always reach out to me over email, and I will try to answer them either on the email or in the next class if we have any. Okay. So, any doubts so far? So, I think I will stop, and we will have some certain hands-on as well. And like, so I recommend you keep your laptops with you, and try to solve the problems along with me. It will be easier to understand that. And so that's it, I think, for today. Tomorrow, Dr. Deep Kiran will be here. I will not be, present tomorrow morning. So Dr. Deep Kiran is basically from IIT Roorkee, and he will talk about non-linear optimization problems and how to solve them. Okay, so he will talk about those problems, and then in afternoon I will be present, and we will discuss something else. So I have shared certain timetable with you. Okay. Just to again remind you that we will have certain lectures, and depending upon like this room here in the academy, and certain constraints are there with this like licenses. So our most of the classes will be 10 to 12 on the week. On certain days it is only 10 to 11, and then 2 to 4 is daily. Okay. And in the Saturday it will be 10 to 1, 3 hours before lunch, and then 2 to 4 is basically after lunch. So 1 to 2 will be the lunch hours, and then we will try to finish the entire course by 14th of Feb. And the quizzes will be on Sunday. They will be open for the entire day, but for a limited duration once you have opened the quiz. So this is it from my side. Thank you.